Today we will do hysteresis curve. There is a process. We are applying magnetizing force with help of current or whatever it is. And magnetizing field what we are applying is H, and the magnetic field developed inside the ferromagnetic material is B. This we have done in the previous lecture. We are making a graph now. In that graph, here on x-axis we take as H, and the unit of H is ampere per meter. On this, whatever is the magnetic field developed inside the ferromagnetic material, we call it B. So H and B, x-axis and y-axis. Okay. What we are doing first, we are increasing H. Based on that, B will also increase. So, let us increase H. What we find that initially when we are increasing H, the B also increase and it gives us this way. And we go on drawing it and we find that it goes like this. But after some time, if we increase the H, then B does not increase, it becomes less responsive, and after that less responsive, and after that we find if we are increasing H, the B does not increase. H in this direction we are increasing, but B in this direction is not increasing. That is saturation point. Now that is H we have already increased. Now we are decreasing H. When we decrease H, we find B is also decreasing, but the same values are not repeated. What we find that when we decrease H, B also decrease, and this decrease in this way, this point, this point, this point, this way. So H decreasing, B is also decreasing, coming down. When H is this much, B is this much. When H is this much, B is this much. So we make a graph this way. And now you see how much is H here. H has become 0. Now when H has become 0, B should also have become 0. But we find strangely B has not become 0. What does that mean practically? Initially when we increase H, 100 domains become straight. Makes a magnetic effect in the ferromagnetic material. They created B magnetic field 100. Okay. Now the H we had applied, that H we decreased back to 0. We removed the H completely. But these 100 which were earlier circles, closed cycles, they opened up, created 100 lines. Then we removed H, this gone, but 2 are still left. Why? Lethargic, inertia, whatever you say. But when we have straightened up 100 lines, we remove our magnetizing force H, we find that magnetic field has not become 0. Some magnetic field is retained in the ferromagnetic material. That's quite normal, it may happen, but we find it happens. H is completely withdrawn, H has become 0, but still this B has been retained there. So this is retentive nature of ferromagnetic material. So this magnetic field is retained. Now what happens? These lines which are retained, out of all these are gone, become cycles, these are still retained. We want that they should also become 0. What we have to do? We apply H in the opposite direction. That H we increase 0 and other value of H. That H value breaks it up. Now B is become 0. For that, what we have to do? We had to apply H in opposite direction. Who made this? This H made this magnetic field. This was H, magnetic field is created. H is removed. Magnetic field did not go fully. This is retained. This happened in ferromagnetic material. It is made of iron. So, some particles still remain like this. To break this up, we apply H in opposite direction, and that also breaks it up. Now magnetic field is 0. How do we show it in the graph? We are applying, initially H in this direction, plus direction. Then we come back. That is, we are decreasing H. It goes like this. Now H is 0, and after that we make H negative. When we make H negative, this B decrease here. Again H is so much negative that the complete B which was retained here has become 0. It is this point. Now H has become successful to break down the B completely at this point. Now what happens? If H is further increased on negative side, then this has become 0 and H is in this direction. Now we increase H in this direction. Now these domains rotate and go in this direction. 2, 4, 6. H is increasing. This is also increasing. Both in negative side. H is increasing in negative side. B also increase in negative side. And we get a graph like this. Okay. Then what happens? We find that after certain time, here this graph become parallel. What is meant that this become parallel? This means that if we increase H anymore, B is not increasing. It has become parallel here. So this is saturation point on negative side. Now what happens? Again we stop increasing the H in this direction and we make it out to 0 again. When we again make it out to 0, then B also decrease. We are reducing H, so B also decrease. This way H is decreasing, B is also decreasing, and this way H becomes 0. When H becomes 0, we find that B has decreased a lot, but it has not become 0. Still it is retained in this direction. This is B and this is H. When H was there, full, B is full. Now H has become 0. So B has also reduced, these two are retained. That is again retention. Here it is shown this retention when H has become 0. After that we make H in this direction. So what happens? These two are broken by this H. Which H? Positive H. So now when we make this H positive, this B has to break up and become 0. So at a certain value of H positive, this negative B has become 0. So graph goes like this. Now we keep on increasing H in positive direction and B goes on developing in positive direction. This way. So this is the path of this graph. Now at a certain value of H, B has become maximum. This is B naught, maximum. Now H again returns. becomes 0, B becomes here. Now H goes to negative, then B goes on decreasing, become 0. Then H goes to negative side, then B goes on negative side. Again H goes on positive side, B follows this route. So this is the route made by this oscillating H and oscillating B. You can make it a smooth curve like this. Now this was initial process that was only for once. But after that, when magnetization, demagnetization start, then this is the path. What is magnetization and demagnetization? This is B is equal to 0, demagnetization. This is magnetization. Now, this is demagnetization, demagnetization, demagnetization. Here. What is the value of B here? 0. Demagnetization done. Again, magnetization in this direction. Magnetization. Again, demagnetization. Again, magnetization, demagnetization, magnetization, demagnetization. So this process goes on within the ferromagnetic material. And this is H, magnetizing force we are applying in the solenoid. So H and B. This graph or this curve is known as hysteresis curve. So in this hysteresis curve, what is happening? Magnetization and demagnetization taking place under oscillating H. If I write this, then H is what? Magnetizing field. Okay. This is what's happening in a hysteresis curve. Now, in this hysteresis curve, the curve showing these changes is hysteresis curve. Okay. So this is hysteresis curve. Now the specialty of this hysteresis curve, first a few important points. Number 1, this value of B when H is made 0, this is retained in the ferromagnetic material and this is known as retention. Retention of magnetism B in ferromagnetic material even when magnetizing force we have made 0. This is retention point, this value of B. So now there is another thing. This retention, we want to make it 0. What we have to do? We have to change the direction of H, make it in the opposite negative direction, and when it comes to this value of H, then B becomes 0. So what we say? We say that this H, negative H has coerced, has forced magnetic field to become 0. This process is known as coercing. You know, coercing, applying a force and making something do. So this is done and B is made 0. This is coercing. Who has done the coercing? H, magnetizing field. So this is coercing point. Okay. So these are two important points in a hysteresis curve. When H will be made 0, when H is removed, how much magnetism is remaining in the ferromagnetic material? This is known as retention. Again, if we want to break down this magnetic field, how much opposite H is required? That is known as coercing point. So, or coercion we can call it. So these are the two important points to understand with reference to when we are going to make them temporary and permanent magnets. Okay, so these are the 2 points. Other thing we need to study. First, I will write the definition of these 2 points. Okay, so here is definition of retention. Retention is that value of magnetic field which remain in the ferromagnetic material. This is important. Remain or retained in the ferromagnetic material when magnetizing force H is made 0. Similarly, we can make a definition of retention. See, coercion is that value of H, magnetizing field, in opposite direction which makes the retained magnetic field as 0. So this is coercion and that was retention. Now after this, another thing, what is the importance of this curve? The answer, importance of this curve is the area within the curve. Area within the curve is this area. Now, what is represented by this area? Area is length into width, is H multiplied by B, and when we multiply H and B, it comes to the dimensions of energy or work done. Okay, so this area represents the work done. Work done in what? Work done in one process of magnetization and demagnetization. One process of magnetization and demagnetization, the work done on the domains. That means if by H we are applying an energy of 100, then what we find that out of 100, 10 is lost in rotating or in magnetizing the material, and what we get on the, what is transformed, what is used is 90. This, again this, we are giving 100, 100, 100, 100. Inside the ferromagnetic material, what we get? 90, 90, 90, 90. Where is the 10 gone? Answer, 10 is gone in the process of magnetizing, demagnetizing, magnetizing, demagnetizing. So that loss of energy is given by the area of this curve, area of the hysteresis curve. This is importance of it. I will write it for you. Okay, so area of hysteresis curve is the work done in process of magnetization and demagnetization. This is loss of energy during each cycle. There are certain machines where we have to do this. Without that, the machines will not work. Motors are there, transformers are there, and all our industry is full of these machines. And in that, every time we are doing magnetization and demagnetization. Okay, so we have to lose energy, that is the demand of the process. But what we want, that energy loss should be as less as possible. So whenever we buy a machine, we ask the manufacturer to supply a hysteresis curve of that machine. Now he is supplying us hysteresis curve of two machines. One is hysteresis curve like this, other is hysteresis curve like this. We have to buy either machine 1 or machine 2. We will measure this area. In whichever case the area is less, we will prefer that machine, because for each cycle the work lost or the heat lost is less. So this is the importance of hysteresis curve. When we see the hysteresis curve has a large area, we will outright reject the machine because the losses are very high. So we want hysteresis area should be as small as possible. This is important. Area should be as small as possible. So this is all about hysteresis, hysteresis curve, its importance, and how do we check it. Again, on the basis of this hysteresis curve, now we are in a position to discuss what is a permanent magnet, what is a temporary magnet, how these magnets feature differently and what are their applications in the industry. That we will do in the next lecture.